Thank you for inviting us. This is, in fact, a joint talk with also Twinkle Jane. So I'll be speaking during the first 2/3 or so, and then Twinkle will talk about the last part, especially concerning CUDA. So I'll start by just saying a little about the title itself. So in our group, we've worked for a long time on transparent checkpointing. And then more recently, there was a breakthrough, an idea on split processes, which allows us to efficiently checkpoint MPI. And you'll see that story later. And that's great. But now if we really want to take this into production, we have to worry about essentially converting calls by the MPI application into other calls that go to the actual MPI library. So that's the sense in which I'm talking about a preprocessor here. And you'll see as the talk develops. So, there. So here's the organization of the talk. First, a little bit about the DMTCP and two keys that allowed us to checkpoint MPI. Then a little more about what we view is the killer app. So spoiler alert, on many batch systems, you can get a 48-hour allocation, but there are certainly some applications that require more than 48 hours to complete. And then finally, we'll get into the heart of the talk, safe, transparent checkpointing and how we want to use MANA as a preprocessor. So let's begin. So first, just a very little bit to say that DMTCP itself is a mature project. You don't want to know what it stands for. Distributed multi-threaded checkpointing. Never let a student name a project, but you Google for that, you'll get only us. And as you can see, it's been used in a variety of fields, not just high-performance computing. But let's get into the two key principles in DMTCP that allows us to do transparent checkpointing of MPI. So here we can do it pretty much across many different implementations of MPI across pretty much arbitrary network interconnects. So the first idea is what we sometimes call process virtualization. The idea is that when we checkpoint and restart, normally we would have a problem. Suppose that the application has saved a process ID, or in the case of MPI, maybe it's saved an MPI communicator ID. Maybe it's saved something that represents an MPI data type. And then on restart, we will be talking not just now to a new kernel, but on restart, as you'll see, we plan to talk to a new MPI library, which knows nothing about any of the MPI constructs that we created earlier. So here we give the example of just an ordinary process ID. And the story is never let a user process know what its real process ID is. So anytime there's any system call going to the kernel, then we always interpose. We interpose in our plugin library. And so here we can see that our plugin library creates a translation table. So maybe the kernel says our process ID is 2652. We update our table and we tell the user that their process ID is 4000. They can later call kill of 4001. We'll do the translation again. And if there is a transparent checkpoint, then the user process has saved the virtual IDs. Then when we restart, on restart, we'll get a completely new kernel and we'll ask the new kernel, what is my process ID now? Then we update the translation table and everything continues to work. So this works fine with DMTCP. It's been a core idea for more than a decade. But now we want to pretend that this is not just the kernel, but maybe the MPI library is out here on the right-hand side. And perhaps we ask for a new communicator, and then we get a communicator ID coming from the library. But I think you can see that we can play the same game here. We can virtualize the communicator ID. We can virtualize data types and so on. So let's go on to idea number 2. So idea number 2 is what finally allowed us to do checkpointing of MPI in a robust way. We had earlier approaches. We had a way of transparently checkpointing InfiniBand directly at a lower level. For reasons that I won't go into, it turned out that that was hard to maintain. And so eventually there was a new idea by a former student of mine, Rohan Garg, on network agnostic transparent checkpointing, which would also be MPI agnostic. So here, the idea, oh, it occurs to me, I might as well show you my face too. Here, imagine that we have the MPI library in the lower half. This will play the same part as the kernel that I talked about. So now we have an MPI application. The MPI application will talk to some stub library, which will then pass calls over to the MPI library itself. And now we can play the same game. Whenever it's time to checkpoint, we will checkpoint everything associated with the MPI application up here, but we'll absolutely not save the MPI library down in the lower half. Instead, when we need to restart, on restart, we will create a fresh application with a completely fresh MPI library. It doesn't know anything about any communicator IDs, special data types, whatever. And then that will restore the upper half. In fact, the lower half MPI library will first start a really small MPI application, but with the correct number of nodes. And once this process knows its correct MPI rank, it'll restore the upper half MPI application that was using that same MPI rank. And everything works as before. In fact, it works so well that we could restart on a different cluster. Maybe the new cluster has a different network. Maybe we switched from InfiniBand to Omnipath. But it's not a problem because the network library is down here. And the only thing that we're saving is the upper half MPI application. So I think now you can see the benefits of this approach. It makes it really robust. And since there are newer networks for HPC coming out every few years, there was no way we wanted to be in the business of supporting every new network. Now the network is in the lower half. Even the MPI library is in the lower half. And as long as they follow the standard API, we're good. So now we see the advantages. Let's get a little closer to the disadvantages. So first, just a quick, more detailed look. So just to make it clear, the MPI application is calling our own stub library. Our own stub library will call into an array of function pointers into libMPI. And here's the MPI down here. On restart, the MPI library will be bound again to the new MPI library on restart, again through an array of function pointers. So the killer application, I think I already gave it away. It's that often we have an allocation of maybe 48 hours, but some applications need more than 48 hours, especially applications that don't necessarily obey strong scaling. So we've been experimenting a lot with an application called VASP, which does not follow pure strong scaling. There are many users who are satisfied with just 32 or 64 ranks, but it takes 48 hours to complete. And that's the sweet spot. If they scale larger, it becomes inefficient. Another example where this is useful is sometimes there are discount queues. So maybe we need to worry about backfill. Maybe there is some large on-demand computation that just arrived, but we still have a few cycles left over for 2-hour allocations. So we could chain together 2-hour allocations, 48-hour allocations, and so on. And so, of course, MPI hardware, the hardware on which MPI runs tends to be fairly robust, but people do want longer allocations from time to time. This is part of actually a 3-way collaboration. It's us in the DNTCP group, NERSC where they have a supercomputing site. Their Perlmutter supercomputer was recently declared to be the #5 supercomputer. And of course, these things change over time. There's a bunch of collaborators. We're also working closely with a company called MedVerge. Separately, another student of mine, Twinkle Jing, she's working on writing her thesis right now, has extended this idea also to work for supporting CUDA, again, using split processes in a similar way. And she'll talk later about the benefits of adapting this approach to CUDA, and even a little about how the two can be integrated to support hybrid computing. So CUDA was more difficult. It's a proprietary software, unlike MPICH. There are certain issues such as the memory is handled differently. The lower half can allocate memory, and then we have to decide who should save this memory, upper half or lower half. There are issues with device addresses, and so on. But please ask her if you have more questions on that part. I'm going to go now to the main part of this talk. This is about how to do transparent checkpointing safely. And here we introduce a concept which, for this purpose, I'm referring to our MANA as a preprocessor for MPI. So the upper half application will, the upper half application will call an MPI routine. But in that stub library, MANA may choose to call a different MPI routine or an extra one. So the issue is this. Here's the problem with the approach that has to be overcome. When we transparently checkpoint, we are only going to save the upper half memory. But what happens if that MPI application is in the middle of making a call to the actual MPI library in the lower half, the one that is talking to the network? Well, then we have call frames on the stack. Some refer to the upper half and some refer to the lower half. It will not work for us to just save the stack because some of those call frames will become stale when we throw away the lower half and save only the upper half. So this is the issue that requires some extra thought. So the goal is to find where is a safe point when we can do the transparent checkpointing. And here we're going to work by analogy with multi-threaded programs. So here it acts as a preprocessor. In a multi-threaded program, we have to worry about deadlock. Deadlock can occur in several different ways. I'll expand on that. We can think of this problem with MPI as a kind of deadlock also. Now, some agent wants to checkpoint and throw away the lower half. At the same time, the application MPI process is using the lower half. So there's a kind of deadlock there where both agents want to use the lower half at the same time. So in order to make the ideas generally accessible, I'm going to describe them in terms of the well-known deadlock prevention, deadlock avoidance, and deadlock detection. And you'll see that MANA, in fact, can be thought of as struggling with exactly those three concepts. By the way, I'll say that currently we're seeing perhaps 1% to 5% runtime overhead, and further improvements are planned. But that's the other concern that I will not talk about here, how to reduce the runtime overhead to make sure it stays really low. And this is on something which is very intensive of collective calls. That's where we're seeing this overhead. But coming back to the main idea, we have prevention, avoidance, and detection. So these are the three concepts that they always teach us whenever they're teaching us about deadlock. So roughly, prevention says, in this case, can we prevent the MPI process from blocking in the lower half? Basically, by forcing it to make a different call. And then if we can't prevent this problem, can we avoid the problem? Maybe by inserting an additional MPI call. And if we cannot prevent it by switching to a different MPI call, and if we cannot avoid it by inserting an extra MPI call, can we at least detect that there's a problem at the time of checkpoint? And then if we can detect it, maybe we can fix the problem at the time of checkpoint. So the issues that we're facing fall very naturally into the same three issues that they teach in an undergraduate course. So let's talk about prevention first. For prevention, we need to try to prevent the MPI process from blocking the lower half. There are two ways in which we take this approach. One is wherever we see a blocking call in MPI, we try to transform to a non-blocking call, and then we add the appropriate plumbing in order to look at what requests are generated and then replay those requests at restart time. So instead of in addition to transforming blocking to non-blocking, we must also do a certain amount of log and replay. In this case, log any requests that were generated and replay them later. Similarly, if any communicators were created, new data types were created, there also we would use log and replay. So there's the idea of prevention. Now, let's move on to avoidance. So sometimes it's not easy to just prevent it through a simple strategy like the one that I described above. So the avoidance strategies turn out to be more subtle, but in the original paper by my former student, Rohan Garg, he came up with this idea of a two-phase commit algorithm. The idea is insert an extra call to MPI barrier before any collective call. So in our wrapper function, we make a call to MPI barrier, then we make a call to the requested collective. And now, luckily, we're in one of two situations. Maybe no MPI process has both arrived and exited the barrier. If no process has exited the barrier, then no process has entered the collective call. Good, now it's safe to checkpoint. We can checkpoint, and on restart, if somebody is still in this MPI barrier, well, that's our call. We can throw it away. We didn't really want it anyway. Or maybe the processes did arrive at the barrier, and some processes even went further and entered the collective call. But if they entered the collective call, that means that all processes have arrived at the barrier. And in that case, that's great. That means that all we need to do now is wait a little longer, and all processes will finish the collective call, and then we can checkpoint. So that's the avoidance strategy. Now, finally, there's the detection strategy. For detection, it turns out that this two-phase commit still has an issue. There are cases where a certain MPI process can be stuck. We'd have to give them free pass. It's not worth talking about here. But in fact, now we're experimenting with a newer sequence number algorithm by a different PhD student of mine, Yao Xu. It's a generalization of clock vectors. It's not using two-phase commit. He does a topological sort on certain clock vectors. We saw how to use clock vectors in the case of collective calls. And again, there's not really any time to discuss this here, but talk to us afterwards if you're curious. So the original two-phase commit algorithm of Rohan had higher runtime overhead. Now we have essentially zero runtime overhead. And now I think is a good time to turn this over to Twinkle Jane, who will talk about the issues for CUDA. Thank you.
Hi, I hope you can hear me. Can you?
Yes.
Okay. Hi. So in terms of, thanks, Jean, for laying the foundation for MANA and CRAC and split process. So in terms of CRAC project, where we are targeting checkpoint and restart for the CUDA application, these prevention and avoidance you can relate to the crash or the correctness, that how you can safely checkpoint and how can you correctly restore any CUDA application. So in terms of CRAC, as Jean has mentioned earlier, that the lower half where the actual CUDA library is present is dynamically linked, and also it's proprietary. So we are a little bit restricted when we deal with the CUDA application or the CUDA library as compared to the MPI application. So what we want in terms of prevention at the time of initialization and runtime is to not let the application's CUDA library initialize instead of the lower half, so that we can expand the lower half at the time of checkpoint and restore a new CUDA library at the restart time. So this is how we prevent having only one CUDA library initialized. And then how we so I think in the previous slide, Jean mentioned that in CUDA, a CUDA library, and it's okay, you can keep it. I'll describe. So a CUDA library is a library that can allocate memory side by side the host application. So you need to make sure that the memory allocated by the CUDA library and the host application do not overlap. They do not overwrite each other. So this is something we take care in CRAC. So this is one of the avoidance points. At the time of checkpoint, we make sure that we do not checkpoint while the control is in the lower half. It's in the device function. So because CUDA is proprietary and we do not have a means of saving and restoring just the device state with a simple API, we do not checkpoint in the middle of the device function. And in terms of avoidance, we do not save any lower half region. However, there are lower half regions where you need to save the buffers. In terms of when the CUDA malloc happens, you have device address, and device address can have content in it, and you need to save those information to restore the library state at the restart time. So, and on the at the restore level, we disable the process level address randomization, so that as I said earlier, we are and Jean described it, that we are throwing away the lower half and bringing a new library. So we want to make sure that this new library is at the same place where we originally saw it at the launch time. So we disable the randomization to make sure the correctness, and then we avoid any crash by replaying certain CUDA calls to make sure that the library state is saved. So Jean, you can probably do the next. And currently we are working on merging these two split process projects, where you can see that MPI Samana project deals with or handle the scaling to the many node, and CRAC can scale to the many streams, so maximum streams and the UVM feature. So we want to leverage these two split process projects, and now we are working towards a new and better, robust and maintainable design of CRAC, which is CRAC 2.0. So we are targeting CUDA plus MPI application in HPC environment. So I guess, Jean, you can take control of the next part.
And so this did that wrong. Yeah, and so we would both like to thank especially people from two groups in particular. So Tony Shellam and Puri Bangalore for their patient explanations of the precise semantics of MPI and the range of design decisions. Obviously, this critically affects how we design this preprocessor. We have to know what to expect from the underlying MPI library when we change the actual calls from the application into something different down in the MPI library that And then finally, Zhenji Zhao for her also support of this work, explaining to us the priorities for user support and her many suggestions after various rounds of testing MANA. Thank you. Questions?
Thank you and Twinkle for the talk. I just want to ask one general question about what happens, and we've talked about this offline, so I'm not asking you a gotcha question. What happens besides copying memory in and out of the GPU right now in your model?
Twinkle?
Yes. So I guess what you are talking about is the memory allocated by CUDA library. For example, CUDA malloc or CUDA malloc manage. Is that correct? Or you are talking about actual device memory within the device? I
think you're waiting. You're stopping between kernels, right? We agreed on. We talked about this the other day on the call. But what do you have to do in order to make your model work now? Do you do more than just deal with the CUDA malloc memory and essentially copies things that are driven by the application? So every library creates every library, or you can just say CUDA library can have let's call them CUDA objects. For example, there is a CUDA texture object or surface object or a CUDA memory like CUDA malloc. So any object that has been created, it creates or it alters the library state. So in along with the CUDA malloc and memory created by CUDA malloc and CUDA malloc managed, you also need to log and replay any active CUDA object that has been created at the time, like while you are checkpointing. So this is something extra you need to replay, but those calls are very less in compared to how many times application call a CUDA malloc and